Okay, so thanks everyone for coming. It looks like we're at about 9 o'clock here, so we'll let more people wander in or not as time goes on. I'm gonna sort of start the session here by just talking about sparse Fourier transforms and their relationship to these two sessions we have on compressive sensing, function approximation, and sublinear-time algorithms. This is the first session early in the morning here at 9 a.m. to 11 a.m. and there will be a second session after lunch at 1 to 3 p.m. So I hope you'll stick around for both sessions and come back to the 1 o'clock session in particular.
Mark, we can only see a black screen right now.
Yeah, only black screen.
Interesting. It is. That's not ideal. Starting off strong here.
Oh, now we can see it.
Okay, that's good. Let me give this another shot then. We have some recording gold for the SIAM folks. Can you see the screen now?
No.
Nope.
Interesting. Okay. It doesn't like it when I go to full screen mode, I guess. Well, let's see. How about if I do this? Is this okay? You can see the screen now?
Yeah.
Yeah, okay. It's maybe not optimal, but I'll, instead of trying to debug for a long period of time in front of everyone here, I'll just go like this. Okay, good. So again, two sessions, this one at 9 a.m., the next one at 1. So I want to start by talking about sublinear-time Fourier algorithms and their relationship to compressive sensing more generally. So I'll do that first, and then I'll go on and sort of show you how some of the later talks in the session and the next session at 1 p.m. today are going to relate to the topics I'll be bringing up as I go forward here. So just a rapid review of the compressive sensing framework. So compressive sensing effectively deals with recovering an element X from a Hilbert space H using a severely underdetermined set of linear measurements. And the way you deal with compensating for the underdetermined nature of your measurements is by assuming that the element X here that you're trying to recover using your linear measurements is close to some geometrically simple subset M. You can call it a model or something like this. And then you try to figure out which types of linear measurements will work for which Hilbert space and which geometrically simple sort of model subset M. What computationally tractable algorithms you can use to actually take that geometric model plus the linear measurements and get a good answer for the X that you are measuring, what sort of theoretical guarantees you can prove, how fast are the algorithms, etc. So in the sort of standard compressive sensing literature going back about 15 years or so now, usually you have Euclidean space, so just Rn as your Hilbert space, and your geometrically simple subset are all vectors which are S sparse, have at most S non-zero entries in them. Later, of course, you can sort of change this, generalize a little bit. You can have Euclidean space Rn and consider other types of geometrically simple subsets for the same problem. So maybe a subset that has small Gaussian width, or maybe you care about a manifold model, and so you assume that this M is a smooth low-dimensional submanifold of Rn, maybe with bounded reach or something like this. So there's been some nice work on that direction. Or you can make H n by n matrices and assume they're approximately low rank and then try to use that information to do something like matrix completion. So the difference here, or sort of the setup here in the relationship to sparse Fourier transforms, is where we have, let's say, L2 functions on 0 to 2 pi into the complex numbers is our Hilbert space, and our geometrically simple subset in the sparse Fourier transform context are functions whose Fourier series coefficients are sparse in S. And here to sort of separate from classical Fourier techniques, you would assume in general that this sparsity is much smaller than the largest frequency with a non-zero Fourier coefficient. So we're going to assume in particular that in the Fourier domain, you have your two largest important frequencies with non-zero Fourier coefficients, and then a lot of zeros and just a few other Fourier coefficients sprinkled in between at unknown locations, right? So sort of rephrase the problem that we have in the sparse Fourier transform context here, compressive sensing context here. We have an unknown function f handed to us by somebody who wants us to approximate it with a small number of function evaluations. Our job is to produce a good trigonometric polynomial approximation with only s non-zero terms. That means somehow we have to identify the important integer frequencies, because these are periodic functions, omega 1 through omega s, which we only know are contained in some interval from minus n over 2 to n over 2. Okay, so we have to, as part of this sort of approach, figure out the points in 0 to 2 pi that we're going to use to sample our function, to acquire our function evaluations. These are going to be x1 through xm, as well as how many of them, this m value we're going to use. And appealing to the existing compressive sensing theory, you would take m to be something like s times log factors of n, because you know that if you do that in this sparse sort of setting, you should be able to get sort of best S-term approximation errors with this minimal number of measurements that will work out well for you. So the sort of different take on the compressive the sort of more standard compressive sensing setup that we have here that one considers in the sparse Fourier transform setting is that you want your reconstruction algorithm to run in this sort of minimal sampling complexity runtime as well. So you would like to have an algorithm which, given your unknown function f, samples it at these values x1 to xm that you've developed, and then manages to also reconstruct this good sparse approximation, all in a runtime that scales like s times log factors of n. Okay, so methods like this are called sublinear-time algorithms because they run faster than the time it simply takes to enumerate the basis functions that could be important to include in your sparse approximation, right? So in the beginning, you hand me an arbitrary f. I have no idea which of these n frequencies are important to include in my approximation. Simply enumerating them all would take order n time, so inspecting them all one by one or just running through them in a list. Somehow I have to do this in a runtime which is faster than that when s is small. So I do not have the time to consider each basis function by itself. Is sort of the interesting take that sparse Fourier transform methods put on this. So a lot of the great earlier work, which I will be not talking about as much as I probably should, but the time is short, is due to Anna Gilbert, Gyodor Indik, Martin Strauss, Muthu Krishnan, and other folks like that who developed the sort of first discrete randomized sort of methods that can achieve things like that, sort of run times of this order, s polylog n. What I'd like to do now, though, is before sort of showing you some other theorems that are more related to the deterministic and explicit setup, is talk about why you might want to do this, what sort of applications are related to this. And this will have something to do with some of the great talks you can expect at 1 p.m. in our second session. So my favorite example of sort of applications where you have this type of Fourier sparsity and it turns out to be important is these frequency hopping modulation schemes, which were, interestingly enough, sort of proposed by a famous Hollywood actress in the 1940s, Hedy Lamarr, whose picture we have here, who had the good sense to, instead of just being happy being a movie star, to be interested in mathematics and engineering. And so she came up with these sort of frequency sparse communication schemes, which sort of work a little bit like this, to show you why a sparse Fourier transform might be helpful. So let's say Lutz and I, my co-organizer, Lutz Kammerer, and I wanted to have a secret discussion about our Minisymposium. So we were both on our yachts in the Atlantic Ocean. I'm closer to North America. He's over closer to Europe. We're gonna sort of talk about them, what we're fishing for, you know, sharks or whatever it is we're doing. And so what we could do is agree on a set of, on a pseudo-random number generator, which is gonna generate frequencies that our radios use as we broadcast and receive our messages to each other. And every second, let's say the radio will flip from one frequency to another and hop around a tremendously large bandwidth. You know, maybe every second, or probably much faster than that in actual life. And so as we're talking, the frequencies are changing for our radios. We don't even notice. We're, you know, enjoying ourselves. And you guys who might want to eavesdrop to see what I'm going to talk about in my talk are frustrated, however, because if you manage to find where we're talking at one particular moment, the frequency we're communicating on, the radio very quickly jumps to another frequency and you lose us, right? So this is annoying. One way that you could possibly get around a problem like this, if you want to listen in on us, would be to employ a very fast method that can take advantage of the fact that at any particular second, the communication we're having is on one sort of small bandwidth, one frequency, let's say, for just talking about it. And so if you have a method that can very rapidly sift through a tremendous set of frequencies in order to find the one where we're talking, then you can quickly find the frequency we've jumped to right after we jump and continue to listen in on us undisturbed, right? So this is one sort of place where speed of recovery in the Fourier domain is important. And there are a lot of other interesting applications where similar techniques and sparse Fourier transform methods have been used, and we'll hear about some of them in our second session at 1 p.m. So please come back for that. So what I'd like to do now is sort of talk about some of the mathematical theorems you can prove about these sparse Fourier transforms, which will require me to bore you with some notation. So again, we have our base problem here. We're handed a function f, and we're told we have to come up with a good sparse approximation for it very, very quickly. We're going to have to assume something about f. We're going to assume primarily that its Fourier series coefficients, f hat here, are in little L1, so they're absolute value summable. So the function is somewhat smooth. We're going to acquire point samples at grid points in 0 to 2 pi that we get to design, and we'll allow for arbitrary contamination of those point samples by noise or, you know, round off errors, anything like this that you happen to like the sound of. And I'll stack those errors into this vector n for noise. So those are going to be sort of arbitrary perturbations. I'll then make a vector of the true Fourier series coefficients of the function for the frequencies from -n/2 to n/2. So I'll stack those in bold f hat. The Fourier series coefficients we're going to sort of ignore, pretend aren't there, are going to be denoted by f hat z minus that interval. So these will be everything that I didn't put into the vector. And fs opt is going to be a best s term approximation to the vector bold f hat. So what this is just taking the s largest magnitude entries of bold f hat and keeping those and throwing out the rest. So it's the best approximation you can obtain by keeping only s non-zero entries. Okay, so here's an example of a type of theorem you can prove for these sparse Fourier transform methods. So it says effectively that there's an entirely deterministic and explicit way of picking some points in 0 to 2 pi where you are allowed to evaluate your function, or should evaluate your function. And then there's an algorithm that'll take those function evaluations and spit out a 4s sparse trigonometric polynomial piece of s, let's call it, which is degree at most n/2. So you get your function evaluations, a sparse trigonometric polynomial is spit out, and it's guaranteed for whatever f you've given me to satisfy this terrible looking error guarantee that we'll talk about in a second. This is a best s term error guarantee with some extra decorations that I had mentioned before. And the number of samples as well as the runtime of the method is s squared times log factors of n. So first thing, this is a sublinear time sort of algorithmic result because when s is small, less than square root of n plus, a little bit, this algorithm is going to produce this approximation faster than the time it takes to simply enumerate the basis functions that might have to be there, right? So it's sublinear in the basis size. Furthermore, it has to recover all exactly s-sparse functions f that I might be handed. So if f is itself a trigonometric polynomial of degree at most n over 2 that only has s terms in it, then when the approximation this algorithm gives back is going to be bounded by an error where this term is 0, because the best s-term approximation to the lowest Fourier coefficients for frequencies between minus n over 2 to n over 2, this is going to be 0. It'll be f hat will be equal to fs opt. Again, this term will be 0 for the same reason. If there are no frequencies outside of the range from minus n over 2 to n over 2, this is also going to be 0. And if I have no arbitrary perturbations or noise on my function evaluations, then this term is also 0, right? So I'm guaranteed to recover anything that's exactly sparse perfectly. And if it's not exactly sparse, then I'll have some sort of graceful degradation in the equality of the approximation that I get. Okay. If you want a hard open problem to think about, you can try to come up with a deterministic and explicit algorithm for the Fourier basis that runs better than in quadratic time. It appears to be quite a difficult problem. It's related to the quadratic bottleneck problem in compressive sensing, except it's that Bourgain and some of his collaborators solved, except it's a bit more difficult because you also need a recovery algorithm that runs in time less than s squared. So I don't know how to solve this problem. If anyone else does, that would be, send me a text about it or something. One way to easily overcome this bottleneck problem, though, is to simply randomize the method, which is a very standard sort of approach. So if you are comfortable with a small probability of failure, you can, in the context of these theorems, take a subset of the same nodes that work for the deterministic algorithm, a much smaller subset at random, and run your algorithm on those. You'll be guaranteed to get the same error guarantee for the output piece of S as you did before, with probability at least 1 minus delta, where you can choose delta to be as you like. And the runtime is now linear in S times log factors and has a small dependence on delta. Okay, so one last sort of thing you can do. So those prior two results were about functions from 0 to 2 pi into the complex values, and I was allowing myself to pick points in the interval 0 to 2 pi any way I liked in order to get a good algorithm and sort of some sort of guarantees for it. If I have a discrete setting, I just have a list of numbers, f, and I want to compute the discrete Fourier transform of this list of numbers. I don't have a function at my disposal, but I can still use the prior results by sort of adapting some unequally spaced sparse Fourier or unequally spaced FFT type of techniques to the problem in order to utilize the prior theorems and get entirely discrete results that have similar sort of best S-term approximation guarantees. And you just end up with this extra term here involving R, which has to do with the extent to which you adapt your methods, your continuous methods to use the discrete data that you have at your actual disposal. So entirely deterministic methods that are S squared in runtime and randomized ones that have this linear dependence on S. Okay, so perhaps most importantly, and these one-dimensional sparse Fourier transform methods work well in practice. Here's some publicly available code. These are serial implementations in red of the randomized method that I was just talking about for the discrete case. And we have vectors that are 2 to the 26 long, and we're running, computing their discrete Fourier transform when we have engineered them so that they're going to be sparse with the sparsity in random locations. So random non-zeros in the discrete Fourier transform. So what you can see here, FFTW is a standard n log n time Fourier transform method, and it doesn't care about sparsity, so it's always going to take about as long. The red curve here is the code associated with the theorem, the last theorem, and you can see it's always faster than a standard FFT as long as your sparsity is less than 4,000 in this particular set of experiments. So you can actually use these things to speed up your computations if you really have sparsity in the Fourier domain and you're working with really large vectors. Okay, so that's fine. Things work pretty well in the sparse case. One might ask whether you can use these sort of same methods for functions of several variables. So let's say now I'm given a function of d variables into the complex numbers on a periodic function on the torus, d-dimensional torus, and you ask me to come up with an optimal S term, near optimal S term approximation in terms of the multivariate Fourier basis. So you can do this by sort of reducing to the one-dimensional case in a nice way. You can just wind the path around, in this case, the two-dimensional torus, or this donut here. And on this path, the function defined on the larger function, but restricted to this path, is going to be a function of one variable as you start from some place and sort of walk around the torus, right? And this function of one variable, it turns out, if you compute its discrete Fourier transform, and if you've constructed this path in an intelligent way, you can take the computation for the discrete Fourier transform or the Fourier transform of the one-dimensional function and unwind it to tell you what the multivariate Fourier basis best S term approximation is for the original function of d variables. So this is just a nice collection of techniques involving reconstructing rank 1 lattices. And if you want to hear more about ways you can use this nice method to do function approximation for functions of many variables, you should again come back to the 1 p.m. session and listen to Lutz Kammerer's talk, where he'll talk more about how to do this type of thing. Here's the one type of theorem you can get if you do that. It has the same sort of deterministic and explicit sparsity dependence as the former theorem. We're learning trigonometric polynomials of d variables here. Same sort of guarantees. The interesting thing here is that the dependence on the number of variables that you have is only polynomial of your function. So if you have a function, and computationally it's better than d to the fourth. So if you have a function of 100 variables and you believe there's some sparsity in the multivariate Fourier basis, you can actually run this thing and get a result in a reasonable amount of time. So it gives you a way of maybe approaching function learning for functions of many variables. The almost immediate complaint I would expect to hear is that probably your function that you have like that is not going to be sparse in the Fourier basis, but in some other basis. So the next sort of set of open questions you might consider is, how do I extend these sort of sparse Fourier transform and sublinear-time algorithm techniques to other types of bases? So here's one easy way that you can do this for the Chebyshev basis. So if you have a function which has a sparse expansion in terms of the Chebyshev polynomial basis, where I'm defining this way in terms of cosines, you notice that if you change your evaluation points, whatever they may be, by passing them through this sort of cosine transformation, you end up getting samples from a function which is now going to be sparse in the Fourier basis, except the sparsity has increased to twice as much as it was before in the one-dimensional setting. And so you can attack problems where you have sparsity in these Chebyshev polynomial bases by just changing the sort of distribution that you're sampling with by passing it through a cosine and then applying a whatever black box sparse Fourier transform method you like. And things work out okay. That's one example of the way things can work. For more arbitrary orthonormal polynomial bases, it's much, much harder to get things to work out that nicely. The next talk right after me is going to be by Autry. And he's going to talk about how to do that, what sort of results you can get in that context. So I hope you'll stick around and listen to what he has to say about that. Then after Autry's done, Alex Townsend is going to talk about, again, sort of polynomial approximation and its interaction with sparsity. So very related. And finally, at 10:30, Bosu Choi will be talking about sublinear time algorithms for approximating functions of many variables when you have significantly more general product bases that you're seeking a sparse representation with respect to than just the Fourier basis. So other ways you can generalize these techniques to more complicated types of bases that you might be after, and where you still want to have the sublinear time sort of behavior. And finally, after you have a great lunch, which will hopefully not make you too sleepy, you should come back and listen to our 1 p.m. session, where again we'll have Lutz talking about rank 1 lattice-based sort of approaches for solving some high-dimensional function approximation problems, as well as really the applications that I discussed being discussed for sparse Fourier transform techniques in engineering. And also in the 1 p.m. Session going until 3 p.m., you'll be able to hear about some randomized Fourier techniques and Johnson-Lindenstrauss embedding techniques and their application to tensor computations, which is also very interesting. So thanks a lot. Here are some of some papers related to some of the theorems I showed you if you want to go look at them in paper form. And I guess at this point, I will let Autry start to share his screen and get ready while I take a few questions if anybody has any quick questions about this stuff. By the way, if you're in the audience and you happen to have a question, you can use the Q&A tool to ask anything that you might want to know about. Okay, all right. If there are no questions, then I will turn things over to Autry and let him sort of start his talk off a minute earlier. So whatever he said.
All right. Thanks. Mark, can you all see my slides?
Yes.
Okay, awesome. So happy Juneteenth, everyone. Thanks for stopping by. Thanks to Mark and Lutz for the invitation. I'm going to talk about sparse recovery for orthogonal polynomial transforms. This is joined both with Anna Gilbert, who's at Yale, and Albert Go, Chris Ree, and Mary Wooters, who are all at Stanford. So Mark actually did quite a bit of the background work for me, but I'll quickly review some of the concepts again, just in case someone just wandered in. So we are looking at the sparse recovery problem, and I'm going to start off with the case where there is basically no measurement noise or no noise in the signal. So here we have some vector x that we are multiplying with some matrix F, so it's a linear map, and the corresponding result y is sparse. So kind of this green thing is where the non-zero values are. And so if you like to think of things in the continuous setting, you could, squinting a bit, think of this as a discretization of the whole process. But the focus of my talk will be on this discrete setting. And just to set up some notation, these are vectors of dimension n, and so the matrix is n by n. Unfortunately, I'm going to switch notation from Mark over here and use k for sparsity instead of s. And Mark already talked about, so in this setting, what I'm really interested in, what we are really interested in is sublinear algorithms. So here, again, you have access to x, and what you want to output is y, and like kind of qualify this a bit. What you have is query access to x, so you can basically, read any entry of x, and you can do it multiple times if you want. And you want to compute the non-zero values of y, so you want to figure out kind of these red regions. And as Mark mentioned earlier, what we are interested is in sublinear time algorithms. So instead of saying k times polylog n, which is kind of the gold standard, we'll give ourselves slightly more room and say any runtime which is polynomial in k log n would be fine. And for the most of the talk, I'm not going to pay attention to the exponent in the polynomial runtime. Now, more generally, you want to handle the case when there is some noise in y as well. So instead of it being 0 outside these kind of large values, which by the way, I'll sometimes refer to as heavy hitters, you also have some small noise over here. And what you want to output is some sparse vector z, which is approximately close to y. And what do I mean by approximately close to? Again, Mark had talked about this, but let me just give you a pictorial description again. So you have, so you notice that z is 0 outside of this area. And so what you look at is kind of the total area under this, the difference between them. And that should be close to kind of this error or the noise in signal y. More precisely, you want that the L2 error shouldn't be too far off, right? So it's within 1 plus epsilon of the best case sparse approximation. So we'll use yk to denote the best case sparse approximation. And again, you have query access to x, and you want to, in this case, output z, which is approximately close to y. And again, we are interested in poly k log n time. All right. And just to kind of make my slides maybe easier to see or parse, I'm just going to focus on the no error case, though everything that I talk about does generalize to the case with errors, but I'm not going to focus too much on that. So if Mark had not given his talk, this question might, for example, be not so obvious for maybe some of you. But as Mark already said, for the discrete Fourier transform, there does exist such sublinear time algorithms. If you only cared about the query complexities, that, for example, you're allowing runtime, which is a linear or polynomial in n, but you cared about how many locations in X you looked up, then essentially fairly strong results are known. So for example, reduction and version n showed that essentially any flat orthogonal transform works. Flat just means every entry in the orthogonal matrix is small. So one of the things that our work does is show that sublinear time, so we are going beyond just query complexity, exists for a fairly large class of functions or these maps F. Now, when I first heard of these kinds of algorithms, so here's the intuition that was given to me. So again, you have y, which is sparse that you want to recover. And what you do is you somehow reduce this k-sparse recovery problem to a one-sparse recovery problem. And then you basically peel off this, kind of subtract off this one sparse part to get something which is k minus 1 sparse. And then, because I'm simplifying this a bit sometimes, and many of these algorithms, you actually recurse from k to k over 2 and so on and so forth. But one of the things that at least intuitively is said is this kind of one sparse step you solve by a black box method. It turns out that in many cases that actually is not how it's done, even though that's how the intuition is presented. So one of our contributions is to show that you can indeed do this reduction for a fairly large class of maps F, but do use a black box one sparse algorithm. And we are also able to come up with one sparse recovery algorithm for, so basically this step using something called the Jacobi polynomial transform, which if you don't know, I'll define shortly. So you get sparse recovery algorithms for transforms that are defined via Jacobi polynomials. So just to kind of give a quick outline for the rest of the talk, I'm going to define orthogonal polynomial transforms next, give you a pictorial overview of sparse FFT, so basically how these algorithms work, because that's kind of relevant to some of our results. Then I'll probably give a bit more quantitative versions of the results. And I go into some technical details, but based on some of the things, when I practice this talk, I probably will not. So we'll see how that works. All right, so let's talk about orthogonal polynomial transforms. So again, this is a matrix F. And the way we're going to represent, say, the ith row and jth column is evaluate some polynomial pj at some evaluation point rj. Now, if I'm allowed to make P arbitrary and the evaluation points arbitrary, this way you can represent any arbitrary linear map. So that's not what we're going to do. We're going to look at what are known as these orthogonal polynomials from a given family. And so we index from 0 to n minus 1, so P0 to Pn minus 1. And we're going to look at the roots of the nth orthogonal polynomial in the family, so R0 to Rn minus 1, and that's how you do it. Now, just to clarify, we actually want this map to be orthogonal, so you actually need to normalize this. You need to multiply it with a diagonal matrix. But that makes the pictures more cluttered, so we're just going to ignore this part. But in the back of your mind, remember that there's kind of a normalization thing going on. All right, so talking about orthogonal polynomials themselves, just to kind of give a quick definition, you can talk about kind of given a measure mu, you can talk about the inner product in the usual ways. And here I'm going to assume everything's between -1 and 1. Of course, you can scale and make it work for any finite region, but we're going to assume we're taking the inner product of any finite region. And given any such measure, it's fairly kind of trivial restrictions, you can always come up with an infinite family of polynomials that's orthogonal under this measure, right? So if I is equal to j, the inner product is 1, and if I is not equal to j, then the inner product is 0 here. Okay. And I'm going to start off by saying one example is DFT, though here I'm kind of cheating. It doesn't quite fall in this thing. For one thing, orthogonal polynomials are defined over reals, where Fourier transform is the complex numbers. But just to kind of show you an example where this kind of framework, polynomial evaluation points make sense. So remember, the ijth entry of the discrete Fourier transform of dimension n is omega to the ij, where omega is the nth root of unity. So one way you can think about this is the jth column corresponds to the polynomial x to the j, and the ith row corresponds to omega to the I. So if you put this in, you get omega to the I. So as Mark already mentioned, people have looked at sparse fast Fourier transforms, like how to solve this problem for this discrete Fourier matrix. And of course, kind of like the first main work here is the work of Cooley and Tukey from 1965, who showed that you can do it in n log n time. So this is kind of the first thing beyond the trivial n squared. Well, this is the best known algorithm if you don't care about sparsity. There was a bunch of work. There's work by Gilbert, Guha, Indek, Muthukrishnan, and Strauss, who did some random sampling and showed that you basically get a polynomial k log n algorithm. Again, there's a bunch of great work, including stuff that Mark talked about. So you can even get deterministic algorithms. Oh, by the way, I forgot to mention, I'm going to mostly talk about randomized algorithms. And then there's the work of Hassanei, Indek, Katabi, and Price, who also gave a sparse Fourier transform. We would notice there are 2 papers with nearly optimal sparse Fourier in them. In the case of Gilbert et al., near optimal met polynomial in k log n. In the case of Hassanei et al., nearly optimal means linear in k times polylog n. And that has been improved in future works beyond that. And I know I'm not an expert in this area, so I apologize if I left your paper out. I'm going to do quite a bit of that in the next few slides, actually. All right, so now one example that really does fall in this orthogonal polynomial transform setup is the discrete cosine transform. And actually, Mark mentioned this. This corresponds to the case where the orthogonal polynomials are the Chebyshev polynomials. And so it turns out there are a few variants of the discrete cosine transform. This is the variant that I'm interested in. And in this case, the jth column corresponds to the jth Chebyshev polynomial. If you know what Chebyshev polynomial of first kind is, that's the version that we are looking at, and then you have the roots of the nth Chebyshev polynomial on the rows. It turns out that any orthogonal polynomial transform can be computed in near linear time. It's actually n times log squared n, and it happens via a careful reduction to the fast Fourier transform of Cooley and Tukey. This very nice work of Driscoll, Healy, and Rockmore. So if you just wanted to compute kind of the entire thing and we're not worried about sparsity, you can basically do it in near linear time. So given all of this, you could ask why orthogonal polynomial transforms or why sparse recovery of orthogonal polynomial transforms. And to tell you the truth, the best answer that I have is essentially why not. So maybe a bit more seriously, orthogonal polynomials actually have tons of applications. So one of the places where it comes up classically is this notion of quadrature or Gaussian quadrature, where it basically says if you are looking at integrals with polynomials of a certain degree, you can replace the integral by exactly by a sum if you're using some corresponding orthogonal polynomials and the corresponding roots. And so this has applications in machine learning. So for example, this work, but long story short, it's a classical thing that has been studied for a long, long time. And again, apologies if I left your paper out, but basically, the orthogonal polynomials are used all over, and it seems like a natural problem. We are kind of trying to look into some application machine learning, but I don't want to say anything because we don't have anything concrete yet. All right, so what is known for sparse recovery results in this setup? And again, Mark covered some of this, but just to cover all the kind of some of the relevant work. And again, here I'll apologize up front if I'm leaving my paper, your paper out. So if you're only interested in sample complexity, that is how many queries you need to make, then sufficiently tight answers are known. So for example, the result of Rudolphson inversion ensure that k polylog n is enough for any flat orthogonal polynomials. There are other results, for example, of the form that the columns are orthogonal polynomials, but now you pick the evaluation points kind of randomly according to this measure mu, and that also works, and so on and so forth. And it's known that basically speaking, k log n is necessary, and there was recent work for kind of showing this for certain Fourier matrices. And so there's also Prony's method, which actually allows you to, if you vary in the exact sparse case, then essentially for pretty much any orthogonal polynomial, you can solve this problem in basically k log n time. And there's a bunch of work over here, including due to Potts and Tash, and there's a bunch of other work. However, if what you're interested in is you want sublinear, but also noise tolerant. So as far as I know, Prony's method, there are no theoretical results that show that they work well under with noise, though there are some experimental results that seem to indicate that they actually do fairly well in practice. So if you are interested in sublinear time as well as noise tolerant algorithms, then the results are known for some Fourier-like matrices. So we talked about the sparse Fourier transform, but there are reductions for OP transforming orthogonal polynomial transforms to sparse Fourier. So Mark just talked about Chebyshev. There's also a work of Hu et al. That looks at the Legendre polynomial things. And there are generalizations that Mark talked about on kind of multidimensional orthogonal polynomial transforms, and Bose is going to talk about that later in this session. All right, so I guess I have like maybe 10-ish minutes. Mark, please stop me and tell me I'm wrong if that's incorrect, but let's kind of.
No, that works. You can have 10 to 15.
Okay, let's split it at 12 so that I don't go beyond too much. Okay, thanks. So let's do an overview of how these randomized sparse recovery algorithms for Fourier transform works. And so the first step or the first idea is I want to multiply kind of left-hand side with some diagonal matrix D. And the property that one property that I need from this diagonal matrix is if I multiply it with this k-sparse vector, I get back a one sparse vector. Okay. Now I have this one sparse vector, say y prime, and since f is orthogonal, it means that there exists some x prime such that f times x prime is equal to y prime. And here, again, when at least intuitive level, the idea is we're going to use a one sparse algorithm as a black box to kind of figure out y prime. And once we have our hands on y prime, we'll subtract it off from y. And so we get y double prime, which is now k minus 1 sparse. So I've decreased sparsity by 1. Of course, I don't know what y is, so I don't know what y double prime is, but I can simulate this by subtracting off x prime for x. And once I know y prime, it's fairly easy to figure out what x prime is going to be. Okay. So now I have a sparse recovery problem on k minus 1, so I can just recurse. And again, as I said, this is kind of like the simplest version of this reduction. There are more involved reductions or clever reductions where, for example, you go from k to, say, k over 2 and so on and so forth. So there are a couple of issues that I wanted to talk about since they're kind of relevant to our work. So first, as I said, for most of the works, kind of the step of computing the one sparse recovery is not is not a black box, but actually you kind of fuse this one sparse recovery with the reduction thing. So it's like a white box or a gray box, as you will. And for like kind of the optimal results of where you get k polylog, and this, I think, I'm not aware of a proof that says you have to do it, but there are reasons to believe that you actually cannot use a black box reduction. But for, if you're happy with like a general polynomial k log n, then presumably you could still do this. The second issue is we're saying we're solving this one sparse algorithm to compute this y prime, which means we need query access to x prime. However, what we have query access is to the original x. Right? So we need to figure out a way to simulate the query access to x prime using the query access or queries to x. So kind of one kind of main conceptual contribution of our work is to kind of show that at least with this poly k-log n runtime, you can actually do the one sparse recovery in a true black box fashion. And I'll hopefully have a quick time to kind of just mention a few more things about this later on. So that's one of the things. The second thing I wanted to talk about a bit more is, because this gives more intuition on how things work, and at the same time also explains kind of the limitations of our work. So again, we want to simulate the query access to x prime using queries to x. So again, as a reminder, we are looking at this one sparse y prime that you get from multiplying f times x by this diagonal matrix D. Excuse me. And x prime is defined as fx prime is equal to y prime. And again, since f is orthogonal, you can flip it around. Excuse me. And define x prime as f inverse of y prime. All right, so here's where we are. Again, remember, we want to figure out access to x prime. So again, we start off with y prime, which is d times f times x, and we want x prime, which is f inverse times y prime, and y prime is this. So I'll just put that back in over here. So for access to access any one entry in x prime, you want access to kind of this whole product. And so let's assume you can do the following. Let's assume you can show that the product of f inverse df actually has this very nice property that all of the rows are sparse. Okay, they need not be sparse contiguously like it's over here, but they have like few non-zero entries, like say roughly k or so. Then what we want to argue is there exists such a diagonal D such that this is row sparse. And note that if this whole thing is row sparse, then to recover one entry of x prime, say the top one, you only need to kind of query the first few locations in X, right? So if this is S sparse, one query here corresponds to S queries here. So if S is small, we are still in good shape. So as a reminder, the two properties that we need from this diagonal matrix D is first, if you kind of multiply kind of a k sparse vector with D, you get a one sparse vector. And also you have this F inverse DF to be row sparse. So let's look at the first property. And let's make an assumption first. So let's assume that magically you're able to randomly permute Y, or maybe the support of Y itself is random to begin with. So it's not worst case. So your all non-zero entries kind of spread out nicely. And now what you're trying to solve is, so we are now in the case where the non-zero entries of Y are spread out, and from that you want to come up with a one sparse thing. So here one idea is you can use what called like a boxcar filter. So the idea is you only have non-zero entries in the first few locations in the diagonal D. And so pictorially what that means is you have your spread out support of the signal Y, and then you have another signal which is say 1 for the first few things and 0 otherwise. And if you do pointwise multiplication, it picks out this non-zero things and kind of zeros out everything else, right? So if you had this kind of matrix D be kind of this boxcar, and this is kind of known as a filter, then you would be done with k sparse to one sparse, right? And again, the second property that you need is F inverse DF is this row sparse. So it turns out if D is this boxcar thing, this actually is true for the Fourier transform. I like to point out here that a lot of the innovation, or a fair amount of the innovation in kind of the sparse fast Fourier things, is to look up with more interesting filters and not just this boxcar filter. So kind of these properties are true for a larger class of filters or diagonal matrices D. And so one of the things that we show is that at least for the boxcar filter, this is actually also true for a very large class of orthogonal polynomials as well. So, however, all of this was predicated on the fact that I could randomly permute Y, which is F times X. And so the situation that I have is now I'm looking at the case where I have this random permutation in the middle. Now, for the Fourier transform, there's this very nice property that if this P comes from a family of pairwise independent permutations, then you can flip them around. So multiplying with the left by this permutation is same as multiplying with another diagonal matrix D prime on the right. And so if I replace that, here's the situation for DFT. Again, the F inverse DF is row sparse. And so now one query in X would be some number of queries to D prime X, but I know D prime up front and I can have query access to X, so that's not a problem. All right, so I'm going to quickly go over kind of some quantitative versions of our results. And I think I will not have time to talk about the technical details, but we'll see how that goes. All right, so kind of the result that we can argue is the following. So I have not defined Jacobi polynomials, and I don't think I have time to do that anyways. But for any orthogonal polynomials that contains Jacobi, for the Jacobi polynomials, and there's some parameters alpha and beta, you have a sparse recovery algorithm against randomized that has polynomial k log n over epsilon query and runtime. Well, I kind of lied. It actually doesn't work for general worst case sparse heavy hitters. You need the heavy hitters to be spread out. So for example, if your heavy hitters are at random locations, then this is true. And alpha and beta being greater than or equal to -1 means we do not capture all kinds of Jacobi polynomials, but this is not that big of a constraint in the sense that many are like Chebyshev, Legendre, a bunch of known named families of orthogonal polynomials fall in this category. So again, the first result is we do a reduction from k-sparse recovery using a one-sparse black box solver for any orthogonal polynomial transform, as long as they have the roots of the nth degree polynomial is kind of spread out, which happens to be true for Jacobi polynomials. And then we give a one sparse recovery algorithm for the Jacobi polynomial transform. The second thing actually is for, well, if sparse, it's by definition spread out, but we need any assumption. So this is kind of the worst case thing. So the kind of more quantitatively, so let's say I can solve the one sparse problem in something like A times n over epsilon. Then what our reduction shows is you can do the k-sparse thing by multiplying it with a polynomial in k over epsilon factor, both in time and essentially query complex. So you need these many calls to this black box, and the rest of the stuff that you do kind of falls in this poly k over epsilon thing. Actually, it's slightly more because we need kind of these the heavy hitters to be, say, at least gamma fraction apart, and that means they get an extra poly 1 over gamma thing. And again, for random k-sparse, gamma is 1 over k squared, so you get like polynomial in k over epsilon thing. And for Jacobi polynomials, we get essentially polynomial log n over kind of epsilon cubed. All right, so as I said, I really do not have any time for technical details. So I'll do the obnoxious thing of just kind of flipping through a bunch of things. There are pictures. Let's see. So again, we want to do this query access to x prime. This is the result we wanted to prove. The thing is, we looking at these kind of filters, which looks like these boxcar thingies, and it turns out that it's not too hard to argue. You basically end up using the Gaussian quadrature result at some point, and then show that actually it's banded around the main diagonal. And the way you do this is by using some standard approximation theory results, like, for example, in particular, Jackson's theorem to do this. For one sparse for Jacobis, it turns out that you can reduce everything to kind of the following problem. You have some unknown angle theta, and what I allow you is kind of noisy access to like cosine some integer times theta. And again, there are issues which actually most of the bulk of the 64 pages is kind of handling these annoying border cases. But again, so we have an approximation like reduction from k-sparse to one sparse, and the runtime is k log n over epsilon over gamma. Open questions, we don't know how to make this beyond DFT, how to go from this worst case k-sparse to random k-sparse. The polynomial dependence is pretty bad, and we want to extend it to Jacobi, beyond Jacobi. And I'm already over time, so I'll stop here. Thanks.
All right, thanks a lot. Great talk. We have two questions. Sergey, you should be able to unmute yourself and ask your question now if you like.
Yes, thank you very much. It was a nice talk. And as far as I understand, all your orthogonal polynomials are continuous orthogonal polynomials taken at some discrete set of points, right?
Correct.
In my research, I use discrete orthogonal polynomials, which are quite different in many respects, especially in complexity and stability, especially in stability of computation. Is anything known about fast orthogonal decompositions or something like that, maybe sparse for discrete orthogonal polynomials?
Good question. I don't know the answer from the top of my head, but the only property that you need is kind of the property that you get from quadrature. In other words, the property that you need is if you're taking the discrete inner product or the discrete inner product of, say, pi, pj, and some low degree polynomials, then as long as I and j are far apart, then it should be 0. I don't want to say something that's incorrect, and that could be true for discrete orthogonal polynomials, and in that case, the proof should go through. But the other piece that would be missing is this one sparse approximation thing for that. So you still have to kind of develop that.
Okay, so it's somehow an open question, at least for the experts. Okay,
Yeah, so the point is currently if you want an end-to-end results, the only thing we can guarantee so far is for Jacobi, and that too for the spread out version. So for other things, I kind of the reduction from k-sparse to 1-sparse is fairly general. And I said it should go through for discrete orthogonal polynomials as well, but you still have to develop that 1-sparse thing at the end.
Okay, thank you.
Sure.
All right, great. Daniel, you should also be able to unmute yourself and ask your question. And Alex, if you could sort of share your screen while Daniel asks his question, that would also be good.
Yeah, thank you very much for the talk. I have a question. What is the arithmetical complexity of your orthogonal transform? You mentioned it's big O of n. Is that true?
No, sorry. It's I should have clarified. I said it's O tilde n, so I'm hiding like polylog factors.
Ah, okay. Yeah, thank you.
Yeah, sure.
All right, great. Then in this case, let's move on to the next talk. So we have Alex Townsend here from Cornell University, who's going to talk to us about L1 polynomial approximants. And to try to stay on schedule, I'll turn things over to Alex now.
I forgot to unmute my mic, which was quite important. So hopefully you can hear me now. So, okay, so I'm going to talk about error localization of best L1 polynomial approximants, and it's connected to compressed sensing. So back in our previous lives when we could travel, I went to Tokyo National Institute of Informatics and went to visit Yuji Nakasukaze, who's no longer there. He's now at the University of Oxford, and stayed there luckily for 1 month. And during that time, enjoyed some pretty lattes, as you can see here, as well as thinking about some problems related to continuous analogs of compressed sensing. So a lot of my work is motivated from Chebfun, a MATLAB system for computing with functions. And one of the general goals there is to take functions on intervals, balls, cylinders, spheres, other simple geometries, and to replace them by a proxy. In this case, in this talk, I'll just focus on a polynomial. The reason that we like to replace black box functions by simpler proxies is so that we can go and do a whole host of fast numerical computations on them. And so, I mean, you could replace your function by the best minimax approximation, the polynomial of degree n, let's say, that deviates least from f on an interval, -1, 1. Or you could take the L1, or you could take best least squares, or you could take a Chebyshev interpolant, a Legendre interpolant, all those things. But one of the things that was a mystery to us before is, and one of the properties that we like about best L1 polynomial approximations, is that they seem to localize error. So here I have a function, which is basically the apps of x shifted so that the discontinuity in the derivative occurs at 1/4. So there's a discontinuity right here on this interval. This is an error plot. The blue line is the error between this function and the best minimax approximation. As you know from classical approximation theory, we have the equi-oscillation theorem, right, which says that the maximum error, the maximum error that this obtains is obtained n+2 times. And more than that, it equi-oscillates between the plus and the minus of that error. So that theorem can be thought of as, that's a beautiful characterization of best minimax. That's a positive way of viewing it. A negative way of viewing it is saying, well, that means that the error is essentially globalized across the entire interval because it must be obtained n+2 times. In contrast, if I look at the best L1 polynomial approximation that I've computed here, it's better than the minimax approximation almost everywhere on the interval, apart from, of course, as it must, it's got a larger, it deviates more than f on a very small interval. In particular, that interval is concentrated around the non-smoothness location of the function. And so these observations go all the way, at least this is one of the earliest ones I found, in 1981, where they often have statements that say the best L1 approximation localizes error. And we wanted to try to explain why. The reason I got interested in that behavior was from a help query that we get through the Chev Fund help desk. We get emails about, can you do this for me? Can you do that for me? And one of them was related to a corrupted function. So here's the application that we will discover is related. So I'm given a function, and I'm imagining all I can do is evaluate this function f. And I know underneath it should be some smooth function plus some perhaps corruption. And I'm imagining that corruption has relatively small support. So here's a setup, an application of this. So up in New Mexico, there's a CO2 detector in this mountain that's recording the CO2 in the atmosphere as parts per million. And here's a detector. It's just recorded over 1,000 days. And each day they take a recording of the CO2 levels in the atmosphere. And so you can see you could imagine this being a relatively smooth function. However, some days they've had issues with the data collection, and they have impractically large values or impractically low values, which don't make sense. They also had two periods of time here where they had lost the CO2 detector. They had turned it off, and I think this was like over some Christmas period, and they've actually had completely missing data. So this you could imagine, G is this smooth underlying function you could imagine here, and omega is this corrupted function here that's corrupting this smooth function. And this is what the best L1 approximation gives you. It, in some sense, is recovering a good approximation to this smooth function because of the way it localizes error, as I will explain. If you do like a best least squares fit that you might imagine, of course you just fit the corruption, and that causes huge oscillations in the smooth part where you expect good data. So this is the problem that got me interested in best L1, and we're going to be using its error localization properties to explain this phenomena. Oh, by the way, just to connect to Atru's talk, this best L2 approximation is computed by a fast orthogonal transform using Legendre transforms. Okay, so here's our setup. So we were trying to understand this, and so we had a feeling that it was connected to compressed sensing. So not quite the compressed sensing we've had with an underdetermined system, but one with an overdetermined system. So say I have an overdetermined linear system here, a tall, skinny matrix A, and I'm trying to find this X. Of course, this is an overdetermined system. There are more constraints than degrees of freedom in this linear system. And I want to solve this overdetermined system so that not the solution is sparse, but the residual is sparse. So that's the difference. Instead of underdetermined with a sparse solution vector, in this setup, I'm thinking of an overdetermined linear system with a sparse residual, which is very closely related. So of course, in the compressed sensing, you might want to, this problem here means you want to solve it in this measure where you're counting the number of non-zero entries in the residual. And the idea of compressed sensing is to change that to the L1 norm and solve this problem instead. And then understand when this problem, the solution to this problem, exactly recovers the solution to this one, or maybe it's near recovery. And so you can kind of see why that's a good idea to change to the 1 norm and perhaps not use the least squares fit from just the unit balls, right? If I give you this is in 3 dimensions. So if I wanted a sparse residual, I might want it to live along an axis so that the other 2 entries are 0. So I'm imagining my sparse residual is at this point here in 3 dimensions. Otherwise, it would just have a lot of 0 entries and lie on a hyperplane that's connected with a lot of axes. So if I take this hyperplane that's being described by this residual, with these are the coefficients describing it, and I try to minimize it in the 2 norm, more often than not, this hyperplane will end up touching the unit ball at a place off the axis and not give me a sparse solution vector. But because the L1 norm is pointy, right, has this shape, as I try to move this hyperplane in, more often you would imagine that often you might get this hyperplane touching on an edge and therefore returning a sparse residual. Of course, to make that precise, one assumption you can make on the matrix A is a kind of RIP condition. So to connect this up to what I was showing you with best L1, we went through some of the classic papers, and you can just like try to derive continuous analogs, trying to get it to a setting where you can understand best L1 in the continuous setting. So every time I see a vector in those papers, I would write down a function. Every time I see, here in this case, an overdetermined linear system with a sparse residual, I'm going to write down what's called a quasi-matrix. So a quasi-matrix is a continuous analog of this overdetermined linear system. Now, the right-hand side, being a vector, is going to be turned into a function, f. This is the function that I actually want to fit. I'm thinking of f as smooth plus corruption. And here on the left is a quasi-matrix. So this is a matrix where every column is a continuous function. And because I want my approximate that I'm going to get at the end to be a polynomial, I'm actually going to fix this to be a Chebyshev basis. This is actually called the Chebyshev basis of the second kind. So if I discretize this appropriately, I would end up with an orthogonal transform. But we're not going to discretize it. We're going to keep it at continuous level. So this has got infinite by n plus 1. This is an infinite by n plus 1 linear system. Okay. So over on this side, we might want to solve this by trying to have the smallest number of non-zeros in the residual. Over here, this is what I want the continuous analog to be. So here I've defined Qn to be this sum. This is what the left-hand side gives me when I do this quasi-matrix times vector product. I get this sum here, which is a polynomial of degree at most n. And I want the residual to be as sparse as possible, which in this sense, I'm going to define as having as small support as possible. Of course, this is a very hard problem to actually solve. So instead, in the compressed sensing trick is to convert this to a discrete L1. And in our setting, we're going to convert that to a continuous L1. So that's the motivation here of doing it. And see what kind of theory we can get from this side to carry over in this setting right here. Okay, so there are many actually infinite analogs. This is just one, which we call the continuous analog, a continuous analog. So, okay, to understand smooth plus corruption, I'm going to make the problem a little bit easier. So instead of this being a function g, any function continuous, I'm going to restrict myself initially to being this g being polynomials of degree at most n. Okay. So what I'm going to do is I've got this function, there's some corruption. This is a function, in this case, I've got a polynomial of degree at most 8. This is this orange, actually. And then I've corrupted it just artificially on small intervals. And this is what's, so the support of my omega here is the support of these obvious corruptions that you can see. And so I'm supposing this support is small, and I want to recover what's in orange. Okay, this in this case, the best L1 polynomial approximation to this blue function of degree 10 exactly recovers this underlying polynomial. So when I have this polynomial, this is where I can make sense of exact recovery. So, okay, so here's the, what you might call in the compressed sensing, like the information theoretic result for this continuous setup. So I have a function, I've got it's a polynomial plus corruption. And it's very simple to show that if you have more polynomial than corruption, by that I mean the polynomial is corrupted on an interval that's less than half the total length of the interval. In this case, when we have an interval of length 2, from -1 to 1, I mean when the support is less than 1, then this recovery of trying to find the best one that minimizes the support is exactly recovering the PM. So this is kind of the information theoretical result. And so here's the PNL0, you might think of, recovery of this corrupted Legendre polynomial of degree n. Of course, this is very brittle. In practice, I won't know that this polynomial here is of degree 8. So I might start picking other numbers, right, and try to recover. Maybe I try like n equals 7. In this case, it ends up matching precisely a little bit of corruption here, instead of actually understanding the underlying thing. So this is brittle if I don't get the n that I'm using to approximate bigger than or equal to the underlying n. Of course, I don't know n. Okay, so here's what you can show in the L1 situation. I'm going to show it's not brittle, and that means we're going to be able to actually take this m to infinity. So we get an exact recovery in a certain situation. So if you have f plus a polynomial of degree m with some corruption, and that corruption happens on a very small interval. It happens on a small interval of size 1 over n squared, O of 1 over n squared. This 1 over n squared is coming from a concentration-like bound on polynomials of degree n. For example, Bernstein's inequality tells you that derivatives, are no bigger than n squared times the polynomial, the infinity norm of the polynomial. So this is kind of where this is coming from, concentration bounds. In particular, this is related to what's called a Remez inequality in the L1. Anyway, in this case where there's very small corruption, you can show that you get exact recovery. So this is identical to the compressed sensing literature when you have if you limit the amount of sparsity, you can get exact recovery. You can recover the sparsest solution in the case. In this case, we can recover the solution with the sparsest residual. Okay, so the rule is if n is big enough to get recovery, and n is not too big. Reason we need n not too big is we don't want to start fitting the corruption. Then you get exact recovery, and this is all kept in this theorem here. Okay. You can go further and show that this L1 is not brittle, just like in the discrete case. So if n is not big enough, let's say n is not big enough for exact recovery. So here I have this polynomial of degree 8, and I've tried to fit it by a polynomial of degree 5. You might hope that polynomial of degree 5, okay, it won't exactly recover the underlying function, but you hope it does as good as possible with degree 5. And that's what we show. So supposing you still haven't got too much corruption, but you've picked n way too low, what you can show by another kind of concentration argument is that the recovery, your best L1 approximation, approximates the PM here almost as best as it can. So here's the error that you actually obtain, the error between this red and this blue function. The best error that you could hope to have got would be the best L1 approximation to PM, right? If you ignored the corruption. And you're a little bit off that depending on this factor, right? Which is related again to the corruption and the support of the corruption. So they're related to the degree and the support of the corruption. And now there's some really weird features that as we looked into this, we got more and more intrigued by. So we proved some more results, which I don't think have a discrete analog. So what you find is that, okay, when n equals 5, you get this near best recovery. When n equals 10, you got exact recovery. As you increase n beyond the limit that you have here, what happens is you start fitting the corruption when n is large. But it's not just you fit any old corruption. You always fit the corruption that happens near the endpoints first. And as you rack up n, you slowly start fitting the corruption that happens on the inside. And we've actually proved this. It's again related to the way that polynomials can concentrate on intervals. So here's the statement. If you're interested in recovery inside -1, 1, so let's say -1/2 to 1/2, so this sigma here is 1/2, this psi here is 1/2, then you can actually reduce the amount of corruption that you can actually increase the amount of corruption that you're allowing. So if you care only about recovering inside a smaller interval of -1, you're actually allowed more corruption in the worst case. So this explains why you start fitting the corruption first, because of this factor here. Okay. And of course, okay, that's the inner corruption. And of course, as I increase n, this bound here starts to be by, you start fitting the corruption that happens inside the interval. Of course, you're still actually missing some corruption because it's in some sense still trying to localize error.
I think Simone might have a question now.
Okay, go ahead. Yeah, please.
Yeah, sorry, I was just asking Mark about the possibility of asking questions to the Q&A.
Yeah, go ahead.
Anyway, it's not
Please,
a problem.
please go ahead. I want questions.
No, there was actually a comment about your connection between, compressed sensing and then looking for a continuous analog.
Yeah.
And I think there might be interesting to investigate also connection with the so-called least absolute deviation, because it looks like closer to what you're actually when you're minimizing the L1 norm of the residual. So I was wondering if you also looked at that literature.
So actually, all these many of these results that we're showing here are related behind the scenes by showing that there's a precise connection to the reproducing to the RIP conditions in standard compressed sensing when you try to recover a sparse residual. One of the things we actually did, if I want to go back, I don't know if I do, but is show that quasi matrix that I wrote down it does satisfy RIP-like condition, and we use that to show that we get sparsity in this case. I haven't actually looked at the absolute deviation literature, but that would be interesting.
Yes, sometime in compressed sensing, it's called a LAD lasso decoder when you have sparse corruptions on the data. Then your statistics sometimes just called the LAD, so the least absolute deviation.
Okay,
That could be highly useful maybe in your context.
Yeah, so that might actually in the end improve the algorithms that I'm going to suggest if I could replace the algorithms I'm going to have with lasso. Yeah. Yeah, that's a very good suggestion. Thank you. I'll take a look. Okay, and of course, okay, when n equals 40, you basically get rid of everything and you're just recovering the corruption as well. Okay, so this is perhaps where the LAD lasso scheme might become useful, is when we actually try to turn this into an algorithm. At the moment, we're using very classical approximation techniques related to what's called Watson's algorithm, which goes back to the 1980s, where he has an algorithm a bit like Remez's algorithm for minimax approximation, but converted to be for best L1. And he has this scheme where he discretizes the problem into a discretized L1 problem, and then solves it in his setting by linear programming. We've actually just changed this a week ago to use to solve a slightly different problem. But this might be where we might be able to replace this algorithm to speed up things. This algorithm is very classical and not necessarily state-of-the-art techniques here. But regardless, this code is publicly available. You just get it through Chevron. And you get all kinds of error localization with this. So here I've taken an oscillatory function, and actually, even though I've under-resolved it, so this cannot be represented accurately with a degree 100, you can see that the best L1 is actually matching the function on as much as it can, and then it gives up in between. Compare that to the minimax, where the minimax approximation just gets it wrong globally. You can see why it's matching the mean here, so that it gets tons and tons of equi-oscillations in the error. Okay, so this is when you let m go to infinity, you end up in this situation, explaining why the best L1 can deliver you this kind of thing. It's almost it's giving you almost the best L1 approximation to the smooth G up to some factors. You can go back to the original Alps of X.
A quick question, sorry.
Go ahead. Yeah, go ahead.
So you said that you generally tend to resolve or start fitting the corruptions at the endpoints before.
Yeah, you always.
You showed one slide back. It looked like you were fitting them.
So actually, you can see here.
Ah, okay, okay.
So you can actually see. So I'm actually just going to explain exactly how this gets concentrated.
Great. Okay, I'll shut up then. Thank you.
Yeah, you can see right here. It's got I've got error localization at the ends too, as well as in the middle.
Okay.
But anyway, yeah.
Yep.
This always happens. So almost always, yeah. So going back to that original of Alps of X, we can now explain exactly why, because you can treat this as Alps of X as a smooth function. Here I've just like Gaussian smoothed this little bump here. So this is a smooth function that polynomials can approximate very easily, plus a small corruption. That's sparsely supported. And this explains exactly this. We're almost getting a best L1 approximation to the smoothed out G up to some factors, plus the corruption. You can actually see this corruption here actually looks very similar profile to this one. So that these are related. You can go on and actually understand how much localization you get. So in the middle of an interval, like Alps of X, we've shown that you get 1 over n, where n is the degree that you're going to use to approximate the function. You get 1 over n localization of the error. So the error gets concentrated in the interval of size 1 over n. And so we've managed to prove that. So 1 over n in the middle. But we've also shown that you get 1 over n squared near the edges. And so here we've taken one example so I can get explicit constants out of a function that's not smooth because it has a square root singularity. But you can treat it as, again, like smooth plus small corruption. And the error localization of the best L1 this time will be like 1 over n squared. Again, related to the way polynomials concentrate on intervals. Right. Okay, so about time to end. So due to some connections from compressed sensing, in fact, if you look at our paper, we use a lot of machinery from compressed sensing. We managed just to translate those into a classical approximation theory context, allowing us to explain one of these small observations that have been existing in textbooks, that the best L1 localizes error. And there's some perhaps modern applications of this with signals and corruption. So if you want to find out more information, there's a paper here that is almost accepted in SIAM that proves all the theorems and demonstrates this. So thank you very much for listening.
Yeah, thanks for the excellent talk. If anybody has questions, please feel free to put them in the Q&A or unmute yourself and ask. It looks like
Alex, so I had a quick question. So when you were kind of projecting it down, you were doing it to the Chebyshev basis. Presumably you could do it in other OP bases as well? And
yes, but there is a very strong reason for using Chebyshev. The Chebyshev basis of the second kind here. And that's because of a characterization for best L1 approximations. Just like equi-oscillation theorem for minimax, there's a characterization for best L1. And it involves Chebyshev polynomials of the second kind. So as we do that, we can actually check if we've already got the best, if we work in that basis. If you work in another basis, you could do everything, but you wouldn't have that characterization to fall back on.
Okay, thanks.
Okay, may I ask a question?
Yes, please do.
Okay, thanks again. It's very nice talk for me. I have a question about the effect near the endpoints. I have some experience with L2 approximation by orthogonal polynomials, discrete orthogonal polynomials, and problems near endpoints, namely absolute attenuation of any outliers near endpoints. Is it well known for L2?
No, it's not well known for L2.
Oh, I see.
It is not well known.
Then my result is sort of new. Thank you. I have a recent.
I didn't know. I didn't issue. We didn't. So I believe it wasn't known for L1, even though it was stated as observations.
Yeah.
And I don't believe it's known for L2 either. Because
Okay.
yeah.
Thank you.
Mm-hmm.
Great, thanks.
Thank you.
Alex, if you want to sort of unshare your screen and maybe let Bosu set up for the final talk here. Bosu, you should be able to share your screen now.
I think I did that. Yeah.
Okay, great. Yeah, so our final talk of this first session is going to be by Bosu Choi. She's currently at the University of Texas in Austin, and I'll let her take it away from here.
Yeah, thank you for introducing me, Mark. I'm gonna talk about sparse harmonic transforms, a sublinear time algorithms for approximating the best test term of in bounded orthonormal product basis of multivariate functions. This is a joint work with my academic advisor, Mark, and Tony from Technical University in Chemnitz, Germany. The motivation of our work came from the application of compressive sensing to parametric PDE problem. So let's look at this parametric PDE. So A is the partial differential operator depending on a bunch of parameters Y. So we have D many parameters. So as Y changes, your partial differential operator changes, then accordingly your solution U changes. So what we are interested in is some quantity of interest depending on the solution. So we can interpret this as a functional on the solution U. Then eventually we can consider this as a function of a parameter Y. So our goal is to approximate this function F as an expansion of some appropriate product basis T. So here this F can be approximated by this expansion. Here, the T is the product basis with some index vector. This index vector belongs to bracket n to the D. Here, this bracket n is a set of integer between 1 and n. And this matches this particular product basis and corresponding transform coefficient C. And we have additional assumption. This index vector, especially the energetic index vector with non-zero transform coefficient that belongs to some small magnitude set script S. So here this small case S becomes the sparsity. And to talk about the product basis more, it can be considered as a D product of one-dimensional basis functions. These basis functions can be Fourier basis, Legendre basis, Chebyshev basis, or other any bounded orthonormal polynomials. Then even this product basis can be a mixture of different one-dimensional orthonormal basis. Then recall our goal is to approximate this function F. Then what we do is we fix the parameter with a random choice of Y. And then we solve each PDE using the PDE solver. Then we can get different samples of F. Then now we can build a linear system. This left-hand side contains the function evaluation of F, and right-hand side consists of phi and C. This phi contains the product basis evaluated at each sample points, and C it contains the transform coefficient. And under our assumption, it has only S non-zero entries. Then in several papers applying compressive sensing technique to this parametric PDE problem, we have two steps. We get these function evaluations, and then we solve this sparse problem to find these non-zero entries of C by using L1 minimization, OMP, COSAMP algorithm, etc. So this compressive sensing guarantees that if the sampling number is this amount, S times polylog in N to the D and S, then we can get the pretty good approximation of this coefficient factor, C. But we also need to take care about the computational cost. In this first step, it takes n times the runtime of PD solver. And in the next step, it takes polynomial in n to the d. Because we are in this high dimensional problem setting, we need to search over this n to the d basis functions to find only a small number of non-zero coefficients. Even we consider some structured sparsity, such as hyperbolic cross, the runtime becomes n times polylog log n to the d, but we still have the exponential dependence on the dimension. So our goal is to overcome this computational curse of dimensionality. So our technique is make the existing COSAMP algorithm faster. In COSAMP algorithm, the support identification procedure is the most costly part. It has its runtime is n to the d. And after that, we need to estimate the coefficients. If we use the conjugate gradient for solving the least square problem, its runtime is s squared times polynomial in dn log n. So this part is pretty fast compared to this support identification. And to make the support identification faster, what we do is use the product basis structure and use some additional samplings. And in the end, what we could achieve polynomial in n, polynomial in S, D and N runtime complexity instead of N to the D runtime complexity for all general bounded orthonormal polynomial product basis. But there is a price to pay. Instead of S times polynomial in D and log n function evaluations, we need to use polynomial in S, D, and N function evaluations. Then before introducing our specific algorithm, we identify the common property with which any support identification will approximate the desired support greedily. That property is called support identification property, in short, SIP. If we look at the definition, here S is the sparsity in bracket n, and beta is between 0 and 1. Phi is the sampling matrix, and A is the support identification algorithm. Here P is the power set, so it is power set of bracket n. And gamma is a function whose function value is between 0 and infinity, and it is 0 as 0. Then the triple phi, A, and gamma is said to have the support identification property of order S comma beta if the L2 norm of V restricted to the complement of A applied to phi V plus E is less than beta times L2 norm of V for all noise vector E and sparse vector V, which satisfy whose its L2 norm is greater than gamma of E. So this implies that if V, vector V is relatively larger than the noise vector E, then this support identification algorithm can recover the majority of the energy of V. And the fact is that this gamma is equal as equal to 0 at 0, this corresponds to we find a lot of energy for the exactly sparse case. And any compressive sensing type of problem is triple. And once we have a support identification procedure satisfying this SIP, then we can build a custom type, another custom type algorithm, satisfy the following theorem. Here, this kappa is the iteration number. This cosample is a greedy algorithm, and delta relates to the RIP constant, restricted isometry property constant. And here, this XS is what we are looking for, the S sparse vector. We approximate this sparse vector using two samples sets, a YSID and YCE. This YSID is for support identification, and YCE is for coefficient estimation afterward. And it is contaminated by some noise, ESID and ECE respectively. Then if we have this triple phi SID A and gamma, which satisfy the SIP of order 2s comma beta, and this gamma of ESID is bounded by this gamma bar. And the normalized phi CE satisfy the restricted isometry property. Then the cosamp with this new support identification produces the following S sparse approximation A with this error guarantee. So here the first term comes from this decreases at a rate of 1/2 as the iteration number increases, and this gamma bar is from the noise vector. ESI is L2 norm, and this not L2 norm. Sorry, so it is more complicated, but we will see the example afterward. I mean, the specific choice of gamma bar afterward. And this third term comes from the least square problem solver for coefficient estimation. And if our support identification procedure has big O of LSID runtime and LSID prime sampling complexity, then entire runtime of this cosamp is LSID plus this second term comes from the coefficient estimation plus this third term comes from the updating the samples in each iteration, and kappa is the number of iteration. And the sampling complexity consists of these two parts, one from the support identification, and second term comes from the coefficient estimation. Then to understand this runtime and sampling complexity, another important constant is this K, the BOS constant. It is a bounded orthogonal system constant. So we want to estimate the size of this K. To estimate the size of this K, let's look at our assumption for the function f of interest. We assume that this f consists of two parts, f tilde and e prime. Here, infinity norm of e prime is less than gamma. And this f tilde is an expansion of this product basis function whose index vector n belongs to I and d. Here, this I and d is the collection of index vectors whose L0 norm is less than or equal to small case d, which is less than or equal to capital D, which is the dimension. And we are looking for the best test term of this f tilde. And remember, this product basis T is a D product of one-dimensional orthonormal polynomials. Then if we define B as a collection of product bases, whose index vector belongs to I and D, then we can define the bounded orthonormal constant K as a maximum of infinity norm of Tn. Then to estimate the size of this, we need additional definitions. Here, this Bj is a collection of one-dimensional bounded orthonormal polynomials. And this is another bounded orthonormal system, so we can define Kj, another bounded orthonormal constant. And this Kj1 is defined as a infinity norm of the lowest order basis. And it is always greater than or equal to 1. And it is equal to 1 for many cases of interest. For example, cosine basis, Chebyshev basis, etc. And also, this Kj1 is less than or equal to Kj. And in many cases, it is strictly less than Kj. And another definition, K1 is defined as the maximum of this lowest order polynomials L infinity norm. And K infinity is defined as the maximum of over these Kj's. Then the BOS constant K is less than or equal to K infinity to the D when this K1 is equal to D, which is true for many cases of interest. Again, for example, cosine basis, Chebyshev basis, Legendre basis, etc. So the important message here is this K does not depend on, exponentially on the dimension D, capital D, but it has an exponential dependence on small d. So now we have all the ingredients to understand our main theorem. So we built a specific sublinear-time support identification. And for that support identification, that gives this triple phi SID, A and gamma, which satisfy the SIP with high probability, and also this phi CE satisfy the RIP with high probability. And if these both properties are satisfied, then we can get the sublinearized cosamp, which has the following error guarantee. And this gamma bar that also appeared in the previous theorem, we chose this gamma bar with this specific value. And to make these properties satisfied with high probability, we need this many samples, S cubed times D times K sub infinity to the 4D times small d to the 4th, multiplied by some extra log terms when K1 is 1. And the runtime complexity is S to the 5th plus S to the 3rd times N times D squared times K infinity to the 4D times D to the 4th times kappa times extra log terms. This result is the generalization of our first paper with Mark and Dr. Kramer. But later, the numerical result will show the numerical result our algorithm acts better than this theoretical result. And to introduce our specific support identification, let me give you one example. Our support identification consists of two parts, entry identification and pairing. And let's assume that we have a priori unknown energetic index vectors, 3 index vectors. We are looking for these index vectors in this n to the 3rd many basis index vectors, possible index vectors. Then instead of searching over all these n to the third index vectors, what we do is finding the entries of each index vector first. So here n1 contains the first entry of these index vectors, and n2 contains the second, and n3 contains the third. So finding these n1 through n3 sets, that's the entry identification. Then we can see that the support of C belongs to the Cartesian product of n1, n2, and n3. So we have 3 times 2 times 3, so 18 possible index vectors to find these 3 index vectors. But however, instead of searching over these all 18 index vectors, we only search over 15 index vectors to make our algorithm faster. And in general, we reduce S to the D in the possible index vectors energy estimation to S squared times D energy estimation. So how we do that is in the next slide. Here, this A, B, and C represents the entry identification, finding N1, and N2, and N3. And in the next step, we concatenate each entries one by one. So in D, what we do is taking the Cartesian product of N1 and N2, then we have 6 possible candidates for the prefix. And what we do is estimate the energy corresponding to these prefixes and choosing the top 3. Then we call this set as P2. And then we take the Cartesian product with P2 and N3. Then again, we have 9 possible index vectors. And then we do the energy estimation corresponding to these index vectors and choosing the top 3. Then you will get the desired support of C. So this is an example of our support identification. So in general, we have to find the D different entry sets in the entry identification. And in the pairing, we are concatenating these entries one by one. Then let's take a closer look for the pairing step, because that part is the most costly part in our support identification. So in each pairing step, we have S squared candidates. And for each S squared candidates, we are estimating the energy corresponding to each candidate. So if our prefix is N tilde, then corresponding energy is defined as L2 norm of the inner product between F and T sub N tilde. Then it can be written as this double integral. And numerically, we approximate this using the double sum. Here, M1 and M2 are chosen as enough to satisfy the restricted isometry property. But to suppress the coherence, this M1 should scale quadratically in the sparsity S, and M2 should scale linearly in S. So we need S cubed samples for each energy estimation. And before I said we have S squared candidates, so we need S to the 5th samples, S to the 5th computation to perform this pairing step. And that's why we had S to the 5th term in the total computational complexity in our main theorem. But however, the numerical test, it performs better than this theory. In our numerical test, we mixed different bases, 3 Chebyshev bases, 3 Legendre bases, and D-6 Fourier bases. And this is for the exactly sparse case with some noise, Gaussian noise. Here we choose capital D is equal to small d, n is 200, and m1 is 8s, not s squared. M2 is chosen to be 4s, and this is the noise level. Then if you look at the left figure, then the sample number scales linearly in D, and the runtime scales quadratically in D. And for each trial, for each choice of D, success rate is greater than 99%. And I want to emphasize that with the naive co-sample algorithm, we need to search over this 200 to the at most 100 possible basis functions, but instead we more cleverly search the 10 or 25 basis functions, which is corresponding to a fairly large transform coefficient. And in the next example, we built this F, which is not exactly sparse in these mixed spaces, but it consists of periodic B-splines and shifted and dilate B-splines. And here D, capital D is chosen to be 10, small d is 4, n is 64, m1 is 4s, m2 is 4s. Then as we increase the sparsity, that means we are adding more expansion terms to approximate this F. Then you can see the relative L2 error is decreasing pretty decently, even though F is not exactly sparse in this basis. So this numerical test demonstrates our algorithm it behaves better than what we have proved in the main theorem. Okay, so this is the end of my talk, and here are my references. Our first paper will appear in Foundations of Computational Mathematics soon, and our second paper is in archives. So if you are interested, then please take a look. Thank you.
All right, thanks a lot. Thanks a lot, Bosu, for a great talk. If anybody has any questions, please raise your hand or enter them into the Q&A. And otherwise, I want to make sure to remind everyone that there's another session happening at 1 p.m. where you can learn about applications and to engineering problems of sparse Fourier transforms, and see some other interesting applications that don't involve function approximation if you didn't like some of these talks as much as I hope you did. So come back at 1 p.m. for the second session. And if anyone has any questions, please ask.
Hi, Mark. Yeah, I would like to ask a question. Thanks again for the talk. And is this parameter gamma related to the truncation error of your function?
Wait for a second. The gamma? Yeah,
so the gamma, is it something that you also need somewhere in the algorithm, or is it just useful for the theoretical guarantee? The small gamma, the truncation error. Like when you have the 22 gamma square root 23s at the very end. So that gamma was a bound for your truncation error, I guess?
Yeah, truncation error, that comes from this E prime.
Right. So is that needed somewhere in the algorithm, or it's not?
No.
Okay.
It is for the theoretical result.
Okay.
Yeah, great. Any other questions before we sort of finish off this first session and hopefully see you back at 1 p.m.?
Yeah, I have a question.
Okay.
So you said that numerically your algorithm is much better than theory, and you showed us the dependence on the dimension, right? But I didn't get the dependence on the sparsity.
Depends on what?
On the sparsity, on
sparsity. S. Okay. So here, theoretically, numerically, theoretically, it depends on S to the fifth plus this much, but Yes. So here, this sparsity, if you look at here, it is 10 and 20, so it is quadratic.
Yeah.
Yeah.
Berkeley, it seems to scale quadratically.
Mm-hmm.
With
Yeah,
it's hard to tell because this is like a log plot, but it looks better than S to the 5th, anyways, which is
yeah.
thankfully.
Sure.
Mm-hmm.
Thanks.
Mm-hmm.
Excellent. Any other questions before we call it a mini symposium and come back at 1?